So good afternoon, everybody. Can you hear me? Okay, thank you so much. Okay, so last week we have a revision on the single-phase transformer. So today we continue to talk about the three-phase transformer. We focus on the difference between the single-phase transformer and the three-phase transformer. I think that you understand that the principles of the three-phase transformer and a single-phase transformer is the same. The difference is that in the three-phase case, we just have one primary coilus and one secondary coilus. However, in the three-phase transformer, very similar to the three-phase systems that we learned last semester. So in the primary, we have three groups of the coilus. In the secondary, we also have three groups of coilus. As a result, we have various types of connections at both the primary and the secondary, making the structures of the transformers complicated. So we have to learn how to analyze them. So here is the contents of these sessions. First, so we have a look at the use of the three-phase transformer. Then we show you the types of the three-phase transformer connections. So very similar to that of the three-phase systems we learned last semesters. So at the moment we will talk in detail about that. And the third point is that how to draw the equivalent circuit and phasor diagrams. Because in practice we have to describe the transformers. So what does it mean by the parameters in the circuit? How to draw the equivalent circuit? So we should clearly define the parameters so that everybody will use the equivalent circuit, understanding the meanings of parameters, no confusions. So that's a convention, right? That actually agreements. The fourth point is that parameter determination. So when we draw the equivalent circuit, we define several parameters to describe the three-phase transformers. There we have several parameters. Good. Several parameters. So how to define by doing test the parameters? Actually, very similar that we're doing the open circuit and short circuit tests. The difference is that we're doing the test. We got the three-phase input, output parameters. Based on that parameters, we can calculate or estimate per equivalent circuit parameters. And lastly, because it is a three-phase systems, so we have talked how to take measurements in terms of the power and how to represent the load impedance. Because in the transformer three-phase systems, we have various types of load connected to the transformer secondary side. So how to describe the load impedance issues? Once again, so the approach we are adopting for three-phase systems, including not only the descriptive, statements, but also we try to use in the phasor, the equivalent circuit, and the power, measurements circuit to show you, the above, concepts. Now we move on to the first parts, the use of the three-phase transformer. Here is the drawings that showing the basic components of three-phase transformer. So three-phase transformer back. So this means that we're using three single-phase transformer to form a three-phase transformer. So usually we call it three-phase transformer back that composed 3 single transformer. So as you look here, so single transformer 1, transformer 2, transformer 3. By connecting the primary 1, primary 2, primary 3 to a 3-phase source, the secondary can also be connected into a 3-phase output source. So here we have some points on the pros and cons of the 3-phase transformer bracks. First, the advantage, flexibility. So this is easy to understand because we have 3 single-phase transformer. So in terms of the transportation, for example, we can one by one transport the single-phase transformer to the locations to be located, and then we can connect them. Flexibility. The second one, we can connect them into different types. So star-star connection, delta-delta connection, star-delta connection, delta-star connection, delta-delta connection. So based on our needs. This is a flexibility. And also, if the transformer has some problems, we just with one phase, we just need to replace one phase, one single transformer, rather than to open the whole transformer. So that's the meaning of the lower replacement or repair cost. So this is the advantage of it. Of course, because the 3 single phase separate to each other, they are strong to the voltage, strong to the interactions of the current between the 3 phase. Disadvantage, obviously, it is space consuming. You have 3 single transformers, and also each transformer has their own losses. Each transformer has their own core materials and insulation materials and the wiring materials. So they have relative bigger internal losses. Also, they have relative bigger or higher cost, manufacture cost, material cost, installation cost, transportation cost. Anyway, so in terms of the high cost per kVA, that means in comparison with other types of the transformer. So for this transformer, if you have 100 kVA rated powers, then per kVA cost is relatively higher. Now, where it is mainly used? So it is mainly used on the commercial and industrial low voltage distributions. So because above, advantage and disadvantage. So it is not used in the heavier power center with the higher voltage. You can imagine, So if the power consumption is very big, and if the voltage is very high, so you use this one economically, it's not good. However, so if it is used in commercial or the industrial voltage distribution side, so each distribution point, the power consumption is smaller, And for convenience, we use the single 3-phase transformer as the 3-phase transformer back. From now forward, we'll be talking about the transformer back. okay, in your mind, you should know a three-phase transformer back means three single-phase transformer connected together to form a three-phase transformer. Okay, so get this concept in your mind. Otherwise, later on, when someone asks you, okay, what does it mean by a three-phase transformer back? And you cannot, right, explain to them. Or even for yourselves in examination or in the exercise, okay, so you again ask me what does it mean by the transformer back? Or you confuse the three-phase transformer back with a single three-phase transformer. Anyway, so a little bit repeatedly I explained it. Okay, so this is the use of three-phase transformer. Now, here we show you not exactly like this, but the meaning of it. Three-phase transformer would on a single core. Okay, as you see here, we have a shared type transformer, or with three arms, one core with three arms in it. So one arm with the primary one, okay, and secondary one. The center arm with the primary, okay, 2, and the secondary 2, phase 2. And the third one, right arm, with the primary phase 3 and secondary phase 3. So, of course, in practice, they can be wound on a single core and different way. What I show here is a straightforward way, very simple way. In such a way, you can see that the primary phase 1 and secondary phase 1 share the same core. As a result, the voltage in primary 1, phase 1, and voltage induced in secondary phase 1 will be in phase. Okay, will be in phase, exactly in phase, because they have share the same, exactly the same, right, flux. Similarly, that the primary phase 2 and the secondary phase 2 that in phase, and the primary phase 3 and secondary phase 3 are in phase. So here I say in phase. In practice, that may be, as I just mentioned, that they may would in a different way, so that the primary and secondary, they have phase difference. Okay, we have phase difference because they can be would a different way. Okay. For examples, that the primary phase 1, half of primary phase 1, half of the primary phase 2, corresponding to the secondary phase 1, and half of the primary phase 2, half of the second primary phase 3, corresponding to the secondary phase 2, and half of the primary phase 3, and half of the primary phase 1, corresponding to the secondary phase 3. Imagine. We can do that, okay? Because we can make in the flux from different phase to combine together to supply to the secondary side. Okay? Theoretically, that's the way. So here is just one type of the three-phase transformer. We have different way. So in practice, they may have not in phase, or in phase. Phase 1 primary, phase 2 primary in phase, or not in phase, or has a phase difference. Okay. Now we come to the advantage of it. Of course, because in comparison with the 3 single-phase transformer, that means the 3-phase transformer back, so it uses less space, less cost per kVA, and with higher efficiency. Okay, no more explanation. A disadvantage, low flexibility, higher replacement cost, because it is very big. In the case of the 3-phase transformer back, for the same rating power, say 1000 kVA, 3 single-phase transformer, okay, each of the single-phase transformer has the size that to provide, okay, 330 kVA. So their size is smaller. So you can transport one by one. Okay. However, when it is a 3-phase transformer would on the same core, then it should be able to supply 1000 kVA as a whole. So the size will be big, the weight will be very heavy, and you have to use a big trucks to transport it. You should use a special crane to lift it. And even if the transformer be located on the roof of a building, not in the basement of a building, particularly for high-rise building, you have to design a special lift to transport the transformer, because it is a useful facility. That's the meaning of it. Secondly, of course, if there are problems inside transformer, even with one coilers, you have to open the whole transformer to replace one coilers. Even for the insulation materials, for the oilers unit, for the insulation gas unit, you have to refill it. Because when you open it, so it is leaked, Is largely used, universal use on high-voltage transmission systems, some on commercial and industrial distribution, because it is high efficiency. It is less cost per kVA, use less space. So in the high-voltage transmission systems, we usually use 3-phase transformer rather than 3-phase transformer back. So that's the second type of the 3-phase transformer. Now, so as we said that primary 3 coils, secondary 3 coils, and we learned in last semester about 3-phase systems. As a matter of fact, in practice, the 3-phase transformer be considered as 3-phase source. 3-phase source. So in the 3-phase systems, we learn about the 3-phase source. But here, that means the transformer. Transformer can be seen as the source. Assuming any 3-phase transformer, you can see as 3 single transformer of the same ratings. Remember this word, same ratings. Suppose that the discussion on the 3 single-phase transformer is applicable. In balanced steady state, then the 3-phase transformer can be considered as 3 identical single-phase transformer. So we can analyze the 3-phase balanced steady state 3-phase transformer as a single-phase transformer. So just looking at one single-phase transformer, and then we thinking that the other 2 phases just has a phase angle difference to the phase 1. The other parameters the same. As a single-phase transformer of 2 coils, each of which can be connected either 9 to 9 or 9 to neutral, thus give 4 transmission connections. So we have the star-star connection, we have the star-delta connection, we have the delta-star connection, we have the delta-delta connections. Okay, we have primary, secondary. So this is similar to that, okay, we learned in three-phase systems. That here, even for the star-star connection, as I just mentioned in previous slide, they may have different groupings of the phase 1 and phase 2. So the primary itself is a star connection. The secondary itself is a star connection. But the primary coilers and the secondary coilers is not one-to-one, okay, corresponding, but a combination. So we can say here we have 4 groups of the connection. For each group, they have different vector. That means the primary and secondary, the phase, okay, will be different. So when you read some books, you will find even for the star-star connection, they may have different, right? Different phase correspondings. But here in this chapter, in this lecture, we just focus, right, the very basic star-star, okay, star-delta, delta-star, and delta-delta connections. Do not talk much more complicated, okay, connections, because our purpose is to show you the principles and their, okay, analysis approach. Okay, now we're looking at in practice how we represent different types of three-phase transformers. First, the star-star connection. As I just said, even for the star-star connection, we have different, okay, vector groups. So here, what I show here is the star-star vector group 0, the very basic groups of it. And as, okay, we have the physical connection, okay, drawings here, okay, we have the shorthand notations in electric schematic, or even like this. In practice, for example, this is a primary side. We have 3 coilers. The starting points of the phase 1, A1, and the ending points of the, okay, phase 1, we say A0. The starting points of the phase 2, B1, and the ending points of the, okay, phase 2, B0. And the starting point of phase 3, C1, and ending points of the, right, phase 3, C0 are all connected to one point, the neutral points N1. Okay, so imagine this is a typical star connection as we show here. So the starting point A1, okay, while the coil 1 and the ending point A0. The starting point of B1 and ending point B0. The starting point of C1 and ending point C0 are connected to the neutral points in N1. So the shape we draw here in a star because we would like it to show in their, okay, star connections. Okay, and also their positions in, okay, the transformers in the space. Okay. Similarly, the secondary, okay, we do not read out the names one by one. The secondary also in star connections. And meanwhile, it is obviously that the primary A1 corresponding to secondary A2, primary B1 corresponding to secondary B2, primary C1 corresponding to secondary C2, okay, exactly. So they are, okay, vector group 0. Now, looking at the left side, these connections, if you making the secondary coilus, okay, A, secondary coilus B, and secondary coilus C are not exactly, okay, corresponding to primary A1, B1, and C2 respectively, then what happened? Okay, so for example, the A, B, C are in, okay, and A, B, C are all in a ring core, those are in a ring core. So the A1 and A2 are not in the same position, okay, but displacement, okay, they will be different, okay. So for example, if 1/3 of the A1 and 1/3 of the A2, okay, comes from, okay, the induction from A1, 1/3 of it from B1, 1/3 of it from the C1. And similarly, for the C2, the B2, 1/3 of it from the B1, 1/3 of it from C1, and 1/3 of it from A1. And the C2, 1/3 of it from C1, 1/3 of it from the A1, and 1/3 of it from the B1, okay, in a ring. Then the input phase angle and output phase will be different, okay, or even half, okay, so they will be different, okay. So that's the meaning of it. Okay, here we just looking at this one. This is one simple case. Okay, the dot here. If you're looking at, okay, the nameplate of a transformer, you'll find, okay, they have a simple drawings there. The drawing showing you the connections transformer, and also for each connectors, they're showing you which connector, okay, corresponding to which connector. So the dot here means the polarity. Okay, primary A1 dot, secondary A2 dot. They are in phase, the meaning of it. So in a practical transformer, if you find A1 symbolized with A1, okay, and symbolized with A2, okay, so A1 connector and A2 connector are in phase, and B1 and B2 in phase, C1 and C2 in phase. N1, okay, is the neutral primary, N2 is the neutral secondary. The primary neutral and the secondary neutral, okay, do not think they are connected together. Okay, they are not. Okay. Okay. Otherwise, okay, primary, secondary, okay, so they're separate actually. And this is the explanations of the star-star connection vector group 0. We have other group, okay, 1, 2, 3. So you may find it from some of the reference books, but not right introduced here. This is economic for the small high voltage transformers, as it minimizes the turns phase and the winning insulation. How to understand these statements? What does it mean for the small high voltage transformer as it minimizes the turns per phase? Now, looking at these diagrams, we have 3 phases. Now, looking at this phase, we have the turn numbers primary 1. Okay. Because it is a star connection, so the voltage, the 9 voltage, okay, so because the phase voltage and the 9 voltage times √3. Okay. So now and the V phase proportional to, right? The turn numbers, you know, the turn numbers in primary 1. Okay. So because the V phase, okay, the turn numbers, because the V phase is smaller. Okay. Now, for example, 380 volts, okay, equal to 220 volts times 1.723. And suppose 220 volts corresponding to, for example, okay, here corresponding to, okay, a 1 volt, 1 turn. One volt per turn. Okay, we have, right? So 220. Turns. Okay. So for each phase, we need, right, 220 turns. If 1 turns, right, 1 volts per turn, we require 220 turns. Okay. Okay. So for a star-star connection, 9 voltage equal to phase voltage times √3. And suppose the phase voltage depends on the turn numbers, okay, here phase 1. For example, if the 9 voltage required is 380 volt, and the phase voltage will be 220 volt. If we using the turns 1 per turn induce 1 volts. For 220 volts, we require 220 turns. Okay, Now, for delta phase equal to V phase. Okay? And V phase depends on phase 1. The numbers phase 1. Next slide. Okay. Next slide. Okay. Then 380 volts. Okay. 380 volts. So that is 380 volts, 9, the 380 volts, right? Okay. So means 1 volts per turn. It requires 380 turns. For the star-star connection, if the line voltage is 380 volts, the per phase turn numbers is 220 turns. For a delta case, if the line voltage is 380 volts, the per phase turn numbers should be 380 turns. So star-star connection, per phase transformers turn numbers less than the case in three-phase delta connections. That's why we have the wording minimize the turn per phase. Okay, so I think you have understood these problems. Okay, that's the meaning of it. So because in star connection, per phase just need to produce 220 volts if line voltage 380. But in the delta connection, the per phase should produce 380 volts if the line voltage is 380. This is examples, but you can get the same for the other types of the line voltage. So if you require less turn numbers per phase, then you can use in the star-star connection. So why we say it is used for small high voltage transformers? So when the voltage is higher, theoretically, we require more turn numbers of windings. So because per turns transformer, the produced voltage, the capability with voltage is limited. Okay, so we need more turns. However, high voltage very high, so the many turn numbers making the transformer bigger. So if necessary, we would like to making the transformer turn numbers less, and meanwhile guarantee the transformer's quality. That's the meaning of it. Okay, now here is an example of the star delta connection. So similarly, this is the star delta group 1, 1. Okay, because we have different combinations, as I just said. For this 1, 1, vector group star delta 1, 1, the primary is connected in star. That means, okay, as we show here, the primary A1's endpoints, the B1's endpoints, and the C1's endpoints are all connected to the neutral endpoints. However, the secondary, that's the starting points of the A2 connecting the ending points of the ending points of the C2, and the starting points of C2 connecting to the ending points of B2, and ending points of starting, and the starting points of B2 connect to the ending points of the A2, just like what we show here. Okay, the starting points of the A2 connecting the ending points of the B2, and the starting points of the B2 connect to the ending points of the C2, and the starting points of C2 connect to the ending points of the A2. So here, once again, the dot of the A1, the dot of the B1 represent their polarities. They are in phase. Okay, the dot of the A1 and dot of A1 and dot of the A2, they are in phase because they are share the same flux. Okay, from the A1 induced to A2. So A1, A2 in phase. Okay, in phase. So looking at here, that the primary star connection A1, secondary third connection A2 here. So A1 per star phase, A2 per delta phase corresponding to each other. Okay, so the 9 voltage for the A1 to B1, and here the 9 voltage from A2 to B2, they will not in phase, right? We are not in phase. They will be different, right? Because the A1 to B1, there, okay, here is the 9 voltage between the A and the B. But here, the voltage between A2 and B2 is the per delta phase voltage. This voltage comes from here. So this voltage, A2 to B2, in phase with the A1 to neutral. So A1 to B1, okay, is lagging the A1 by 30 degrees. Okay, this one lagging it. So that's the difference. That's different. Okay. Okay, so this is a very common transformer connection for supply network. Generally, in supply network, the third connection before the high voltage side, the star connection before the distribution side, so that we can using the 3-phase transformer and 3 single phase with the neutral points. However, for the high voltage side, so it is direct connection. The advantage of the direct connection in the high voltage side, which can minimize the harmonics from the low voltage side, the loading side. Okay, star connection side, we used to connect it to computers, motors, and whatever chillers and drills, whatever. So these loadings, not pure resistance, and they have the inductance. As you know that when there is inductance, capacitance, so they may have changed with times, change with the current. So making the systems non-linearity. So this non-linearity in the loading side may induce harmonics. So such harmonics can be minimized within the dirt connections like this. Okay, so the dirt connections in the harbor side, okay, can minimize the harmonics impacts. So from this point of view, such a connection can cancellate the harmonics from the loading side to the systems. Okay. Once again, this is just one type of the star-dirt connections. Okay, here we have the delta connections. Once again, here is the delta vector 0. We have other types of it, as I just explained, for the star-star connection, not repeat of it. So anyway, here, very simple that the primary connected in a delta connection, the secondary connected in a delta connection. You can check one by one that the primary aiding points of the A1 connected to the starting points of the B1, and aiding points of the B1 connected to starting points of the C1, and aiding points of the C1 connected to starting points of the E1, just like a circle. So that's what we draw here. Similarly, for secondary side, the aiding points of the A1 to the starting points of the aiding points of A2 to the starting points of the B2, and aiding points of the B2 to the starting points of the C2, and aiding points of the C2 to the starting points of the A2. That's what we draw here. Once again, the dot represent the same polarity between the A1 and A2. A1 and A2. They are in phase. So as a result, this in phase with this, this in phase with this, and this in phase with this. Okay, so generally, delta connection, this suits large low voltage transformers, and it requires more turns per phase of small sections. A large low voltage transformers. That means there we use big powers, very big currents, big powers, but at the user end, right? At the user end, so the voltage is lower. So suppose one winding can start with 1 volts. So 220 volts, just 220 turns. If we're using the star connection, just 220 turns per winding. If we're using the dirt connection, we can up to 380 volts, 80 turns per winding. So we making the turn numbers larger. Okay, that's the meaning of it. When necessary, when a little bit more turn numbers per phase required, we use the delta connection. When less turn numbers per phase required, we turn to use the star-star connection. Okay, so anyway, so we have different types, the star, delta, star, and star, delta connections. Now we come into the third points, how to draw the equivalent circuit phasor diagrams of it. Anyway, a three-phase transformer can be viewed as 3 single-phase transformer, each of which consists of identical primary and secondary coils. So the voltage and currents will be identical. except of phase shift of 120 degrees. If both side and load are balanced and symmetrically distributed, then it is possible to use the per phase equivalent circuit for analysis. Okay, so if it is a balanced systems, more or less a balanced systems, then we can using the per phase equivalent circuit for analysis. So in the per phase equivalent circuit, every parameters, everything in the per phase equivalent circuit is related to the phase quantity, not line quantity. Phase current, phase voltage, phase powers, okay, phase impedance. Okay. So all is the per phase values. That's the meaning of it. Okay. In the equivalent circuit, when we describe a equivalent circuit, the values given in the equivalent circuit is the per phase quantities. Another point is that any delta star circuit can be transferred into a star-star circuit, okay, without affecting the voltage and current outside transformer. Outside voltage and current outside transformer usually be measured Okay, so these words mean that generally we describe a transformer in practice. For a three-phase transformer, we used to use the line values rather than the phase values to describe the transformer in practice. Okay, so if the line values, okay, the transformer 9 voltage, 9 currents, are the same, then we say this transformer are equivalent. So, okay, equivalent. So keeping the line values be the same, we can using the delta star, okay, equivalent circuit or star delta circuit represented each others, as we learned in last semester for three-phase systems. That's the meaning of it. Once again, so here, okay, if we have no special, okay, explanations, we're using the star phase to represent a three-phase transformer equivalent circuit. Unless that you say now we're using the practical per phase parameters represented. Otherwise, okay, it means the per star phase values. For example, here, a typical example in Hong Kong is the delta star connection, as shown below. As I just said, that the high voltage side is a delta connection, the low voltage side is a star connection. Looking at it here, so the high voltage side, the line voltage 11 kV, and the turn numbers per phase is N2. Impedance per phase is Z2. Okay, now the star connection, low voltage side, so the turn numbers per phase is N1. The impedance per phase is Z1. And the per phase voltage is 220 volts, while the line voltage is 380 volts. There are relationships between the primary phase and the secondary phase primary line and secondary line a little bit different. Suppose for the A phase in secondary, it is in high voltage side is 11 kV. So 11 kV high voltage side direct connection for phase all 9 the same. Okay, because this is direct connection. Now in the low voltage side, there is a per phase value 220 volts. So this 220 volts is in phase with the 11 kV. However, the 380 volts is not in phase with 11 kV. 11 kV. Okay. Similarly, if the primary A1 9 currents, which is the A1 phase currents, okay, A1, then so the A2 9 currents, which is the A2 phase currents minus B2 phase currents. Okay, that's the difference. That's the difference. Generally, the low voltage side currents is larger than the high voltage side currents. Okay. So here is the relative vectors phase angle difference between each other. And the turn number ratio here is N1 phase 1 low voltage side, N2 phase 2 lower side, high voltage side will be 220 volts over 11 kV. But if you're talking the 9 voltage, there will be 380 over 11 kV. That is the transformation ratio. So here, so you look at transformation ratio and phase turn number ratio, not the same. Okay, so to clarify, some students, the transformer ratio in this three-phase transformer. So the transformer ratio is 380 volts, 9 low voltage side, 11 kV, 9 high voltage side. Note 220 volts over 11. Note N1 over N2. Sorry. So not N1 over N2 because the N1 and O2 here. So one is the primary star phase, the other one is a secondary phase, delta phase. So but they're related. Okay, so not but related. You know, what's the relation, right? Okay, what's the relation? So in practice, sometimes they give you the primary phase turn number, secondary phase turn numbers. Okay, so ratios of turn numbers, not always the transformation ratio. Okay, so pay attention to these wordings here, making the things be clear. So in such a way, so we can, for the low voltage side, star calculation, we can take in one phase here, Z1 as per star phase. For the high voltage side direct connection here, we can transfer it into star connection, then take one star phase connecting with the primary star phase to form an equivalent circuit. So delta transfer to star, then take one phase out to form a per star equivalent circuit. Look at it here. Here is a per star phase equivalent circuit for a star delta connected three-phase transformer. For the low voltage side, it's a direct star connection. We take one phase out. So the phase voltage is 220 volts. The phase current, that is also the line current, we suppose R1. The per star phase impedance, low voltage side, is Z1. And the secondary, the high voltage side is a direct connection. And per delta phase impedance is Z2. When changed into a star connection, and you still remember that the per star phase equivalent and per delta phase equivalent, their relationship. So the delta impedance, okay, is 3 times the star phase per impedance when they are equivalent. So the delta per phase impedance Z2 times 3 is the equivalent star phase impedance. So that's we have this one. Okay. So a star connection with the impedance values of Z2 over 3 per phase, and also a phase voltage values, that is the high voltage side, 9 values, 11 kV. Change into the per equivalent star phase, that's 11 over √3. Okay, √3. Then the per phase equivalent circuit is as following. Refer to low voltage side, and here the V2 here is the high voltage side per star phase values. Okay, per star phase. So V2 over 11 over √3 kV per star. So here is the per star to star connection equivalent circuit. Okay. That's why with the low voltage side keeps, which is a star connection, the high voltage side with the delta connection. We have to change the delta connections into a star connection. So their values, okay, the meanings of each parameters and the relationship between the per star phase and per delta phase and the non values. Okay, so in your mind, you should have very clear linkage between the per star phase, per delta phase, and the non values. Okay, they have a relationship between them. Okay, here, so the per star lower side, per star higher side has a transformational ratio. So the ratio A here is V1 over V2. Here, V1 is 220 volts. V2 is 11 over √3. you look, this keeps no change because get star star, or dirt dirt, or 9 to 9. So a okay. Okay, look at it here. There's no change in practical. So the transformer ratio is the low voltage 9 voltage over the high voltage 9 voltage, which is 380 over 11 kV, which can be theorized in 220 over 11 kV over √3, right? Okay, so because the 380, that's 220 times √3. So which can be here is the V1 over V2, right? So the equivalent circuit, the meanings of the transformation ratios no change. Okay. So first, making the secondary be a star connection. So taking the one phase values, drawing in the circuit. Secondly, that making the values up by a squared for the impedance. That refer to lower side. So the current lower by a transformation ratio A, and the voltage up by transformation ratio A. Okay, so that they are equivalent to each other. So here is the per star phase mutual impedance, excitation branch impedance. Looking at this per star to star phase equivalent circuit, and that in relation to the previous slide, the actual star delta connections. You should understand the relationship later on between the per star phase values and the actual phase values in delta or star, and even the 9 values. Should understand okay, so here, although we just give you one examples, but so by reading these two slides, you should understand the relationship, relations between the per star equivalent values and the actual phase and the 9 values. Phase 9 values. So depending on whether it is originally it is a star-star connection, star-delta connection, delta-star connection, and our equivalent circuit always be a star-star connection supposed. So then, based on the equivalent circuit, we have some values there. You should that this per star phase values relate to the per phase or line values in practice, depending on the practical connections of the transformers. Okay, you should clearly understand the relationship. At this moment, some students may got the points, but when coming to the exercise or when in the examinations, or even in the practice, they may confuse some things. Okay, because then with the times, they may throw away what I taught today. Okay, so very short, right? 2 slides, but I would like to convey to you very important information about the 3-phase transformer. Okay, now once again, in single-phase transformer, we talked about the per unit systems. In the 3-phase transformer, we also using the per unit systems. But once again, actually, per unit system be actually once again very similar to the per star phase values, per star phase rating values, for the impedance. Look at here, generally for the 3-phase transformer, we have the 9 voltage. So the rating 9 volt itself can be used as the base of unit. It has the 3-phase total powers. So the total powers is the same for primary and secondary, which is looking at the base values. Now, for the base values of the impedance, so this is the per star phase values actually. So the base impedance values So the base impedance values, actually, look at here, you're using the 9 values square over the 3-phase total, right? Total powers. So now, suppose it is a star connection. Okay, it's a star connection. The phase values, the phase values. That is the times Okay, so look at here. So as what we write here is that the impedance base values is the 9 volt square over the total three-phase powers. So three-phase powers. And suppose it is a right star connection, then the 9 voltage, that is the phase voltage times √3, the square, and over the single phase powers, with three-phase powers, single phase powers, times 3, that's three-phase powers. So √3 squared, that will be 3. So the 3 cancel. So we become the V phase values voltage square over the per phase powers. So per phase voltage square over per phase powers, that is the per phase voltage over per phase currents. That is the per phase impedance. So this phase impedance is the star phase impedance. That's the meaning of it. Similarly, this can be applicable to loadings. So loadings also use a 9 voltage square over the total powers. That's per star phase value. Per star phase impedance. Got it? Okay. So I'm using this one to prove of it. Okay, now we're talking about the determination of the per star phase parameters based on open circuit and short circuit tests. First, when we're doing the open circuit test and short circuit test, what we can measure is the 9 input voltage, 9 input current, and the total three-phase powers outside the transformers. Okay. Okay. So pay attention to these statements that for a three-phase transformer, what we measure are the 9 voltage and the 9 current values and the total power in open and short circuit tests. Okay, remember, because we have no means to measure the per phase values. Even we do not know the transformer's connection. We just take measurements and the lines connected to the transformers. Okay, so then we assume that the transformer is a star-star connection. We can estimate, okay, Okay. The second point is that, okay, so then we assume it is a star-star connection and estimate the per star phase parameters. That's the meaning. Okay. Now, we can do in the open circuit test for excitation branch. So here, once again, we should measure the are you still remember that how doing the open circuit test for a three-phase transformer? For three-phase systems, right? Actually, so generally for a three-phase transformer, okay, when doing the open circuit test, we generally apply, okay, generally making the high voltage side be open. Because high voltage, okay, the voltage required very, very high, so we have no such a source. So making the high voltage side be open. Okay, and to be monitored by using somehow the voltmeters. Of course, okay, the voltmeters cannot be directly connected to the high voltage side, but we are using some a kind of the measurements, right, coils to measure it. And then we gradually apply rating voltage to 9. Okay, the rating 9 voltage to the low voltage side of the three-phase transformer. Okay, we have 3 9 voltage. Okay, so all the 3 9 voltage be applied so that the systems be balanced, and not just 1 9. The other 2 is opened. Okay, okay. So we got the 3 9 voltage, okay, applied to the low voltage side, and monitor the online input currents. Once again, 3 input currents. So 3 9 currents. We can get to the total input powers. Okay, the total input powers can be measured using the 2R meter method. 2R meter method. Okay, so 2R meter method to get the total powers. This is the open circuit test. You got powers, and this is the 9 voltage. Okay. Okay. So line current, purely okay. Here once again, I would like to emphasize the difference between the single phase, three phase. The power first, the power is the total powers that can be obtained using the 2R meter method. So if someone asks you to drawing a diagram showing you how to make the three-phase transformers open circuit test, you can drawing in such a way. So actually, we learn how to draw in the 2R meter method in the three-phase systems when we learn master semesters. Okay, here is application of it. And also, the 9 voltage, usually the rating voltage actually applied. And the currents, that usually is 9 currents. Here, for open circuit tests, the voltage input usually is the rating voltage, and the current you measured is a small portion of the rating currents. That means the excitation branch currents, actually. Then, we assume that the system is a star connection. As a result, in the star connection, the 9 voltage, and over root 3 is the phase voltage, and the 9 current is the phase current. So V open circuit value over 3, that's phase value, or the phase current is the per phase impedance. This is the dominant by the excitation branch. Star phase impedance, dominant Okay, so the this is the per star phase impedance, which equal to the per star phase voltage over the per star phase current. I just explained that what you measure is the 9 values. So in your mind, bear the relation between the 9 values and the star values and the per phase values in the star connection. So here is the per star phase impedance dominated by the excitation branch. So, and here is the excitation branch in series. Once again, so highlights that. So dominant by the excitation branch, not exactly equivalent, right? So what we ignored here, so imagine, actually we talk about this one several times in the single phase transformer. And here, so therefore, this is the series excitation branch circuit, equivalent circuit. So you can change it into parallel equivalent circuit. You know the series values? Okay, so because then when you go to the voltage current, you also have the you have the powers. You also have the power factors here that use angles here. So you can estimate the impedance angles by comparison the impedance values and the powers, and the current voltage, the direct products of the current voltage is the S, right? So this is the power factors. Okay, so this is the open circuit tests. And similarly, for the short circuit tests, we generally making the high voltage side, a low voltage side be short circuit. The high voltage side is supplied with a small portion of the rating voltage, so that the current flows in the circuit be the rating currents. Generally, once again, that both all the 3-9 voltage and 3-9 input currents be monitored, and the total powers input be monitored in such a way that because the short circuit issues, that excitation branch currents can be ignored because the voltage be lower than the rating voltage. The most of the input powers be supposed to be consumed by the internal resistance. Okay, so meanwhile, that the impedance per phase be dominant by the internal coil's impedance rather than the excitation branch. Okay, so that's why here we just said that while in open circuit test, that the power is dominated by the excitation branch, that is the core losses, and a rating voltage, right? So here that the of course it's 9 values, okay? Okay, so that's the difference, okay? I just write down the difference between the left and right. So for short circuit test, that of course the input measurements are all the 9 values. That's the first one. Second one, that the power's input is dominated by the copper losses because the generally the high voltage, low voltage side is open short circuit. High voltage side is supplied with a small portion of the rating voltage, that letting the currents flows on the transformer is the rating currents values. So in such a way, you can determine that the copper losses and rating currents, as well as the internal impedance per phase, per star phase of the transformers. In such a way, you can determine the transformers per star phase parameters, as well as the equivalent circuit. And someone here may mention that you just got the per star phase equivalent impedance, which including both the primary and the secondary. How can I draw the primary secondary separately? As I just actually explained, right? So in the tutorial sessions, in most of the case, the design of the primary and secondary transformer making the primary and the secondary transformer, because their ratings, voltage, and current and power, okay, current is different. Okay, for turns, okay, voltage different. Okay, so therefore the coils, okay, choosing of the coils, making the impedance have certain relationship. Generally, the making the two-side impedance in the equivalent circuit the same, half. I mean, in the equivalent circuit the same. In practice, of course, depends on the transformation ratio A squared. Okay. For examples, if your transformer primary and the secondary transformation ratio is 10, so the primary side, if the primary side, the impedance is 10 ohm, the secondary, okay, will be is 0.1 ohms. The 0.1 ohms, because the secondary times the A squared, for example, turn squared 100 will be 10. Okay, so in the equivalent circuit, both sides will be 10 ohms and 10 ohms. But if the ratio, transformation ratio is 10, okay, 10 ohms and 10 ohms. However, so in practice, the primary, when you measure it, is 2 ohms. Okay, the secondary, when measured, is 0.1 ohms. Okay, times, okay, 10 squared, that's 10 ohms, right? That's the meaning of it. Okay. So this is the open circuit and short circuit, because you have the fundamentals of the single phase transformer, where we have detailed, right, explanations of how to carry out experiments. Here we just write down, okay, the important points here with explanations. Okay, so for the impedance of a transformer, the internal impedance, usually by taking measurements, we got the impedance, and then we convert the per phase impedance into the per unit, okay, value. So then in the specifications of the transformer, just has the per unit values, say 0.5, okay, 0.05, that means the percentage. Okay, percentage. So when you go to the per unit values of the transformers per phase, then you first to get the base values of given three-phase transformer, as I just said. The base values as the per phase values, okay, actually is the per phase values actually. Okay, based on the per phase rating values, you can go to the per phase values. So then the base values, okay, per unit values given transformer, say, okay, 5%, okay, you times the base values, that's the real values in ohms. Now, the base values refer to primary or refer to secondary will be different. Okay, so obviously, looking at here, so the primary and secondary, their rating line voltage will be different, right? While the power is the same. So the base values, primary refer to primary, base value refer to secondary, will be different. So the per unit values is the same. Per unit value is the same. But the base values when you use in the primary, so this is referred to primary values. When you use in the secondary, this is referred to the secondary values. Okay, so do not make confusions about this one. Make everything be clear. Generally, in the practice, in the exercise or in the examination, okay, I will ask you clearly, okay, to get the values referred to primary or get the value referred to secondary. Okay, so every year we do have students confuse this one. So I ask them to get the values referred to primary and also referred to secondary. They just give one. Okay, that's all it. Okay. Anyway, so this slide very important. Okay, showing you okay the difference between the single phase and the three phase. Okay, you take time to digest this one. Okay, digest this one. If you still have some unclear points, you can write to me. Okay, about the three phase systems. And also we will have the tutorial sessions, so ready to answer your questions in that moment. Now we go ahead to see the last slide on these chapters. Okay, a three-phase transformer can be connected to three single-phase transformer or a three-phase transformer. For example, a three-phase induction motors. So if we have a three-phase loading connected to a transformer, the per star phase impedance of the loading okay, so ZL here is the per star phase impedance of a three-phase load, which can be using the looking at here, so 9 rating voltage square over the A's, right? So here that's the meaning of it. The same things. So here is the impedance angle. That impedance angle comes from the power factors. If the power factor is given, you can gauge the impedance angle theta. That's the meaning of it. Okay. For a given load, if it is given the total three-phase powers of loading, rating power loading, and the rating voltage of load and power factor load, this usually be given in such a way by the following equation. Then you can find out the per star phase impedance of a three-phase load, which the values depends on the 9 voltage square over the apparent powers of load or the real powers of load. But you know that apparent powers times the power factor, which is the real powers. Okay, its values. So if the power factor is given, the impedance angles. That's the meaning of it. Okay, because the so the real powers, total powers, their relationships. The ratio is the power factors. This is for general case. Now, for capacitance, here is the for capacitance. If it is a three-phase capacitors. Okay, this is the line rating voltage of the capacitor. This is capacitor's reactive powers, total capacitor reactive powers. Okay, three-phase one. This is the per star phase impedance of three-phase load. Okay, capacity. Because the capacitor is reactive power, so this is rating reactive powers. This is rating 9 voltage. That the impedance angle, of course, you know, is a minus 90 degrees. Okay, minus 90 degrees. That making the current leading the voltage by 90 degrees. So the impedance given above is the phase values for the load connected in star connection, of which is in transformer into the star connection. So that's what I write here for star phase impedance of a three-phase load. Okay, I write it here. So making your eyes, okay, link this sentence together with this, okay, formulas. So okay, so this is right. So the three-phase transformers. So that's the end of today's lectures. So hope you have a good understanding of the three-phase transformers, particularly so the difference between the three-phase transformer and a single-phase transformer. And this stage, right? So and making your own be okay, fully understood with the three-phase transformer. And so we have right tutorial sessions next Thursday afternoon, and we have several examples. Firstly, on the practical single-phase transformer, and then on the three-phase transformers. Probably the next week, maybe depends on the progress. Okay, so this is the end of the lecture, but we still have a few minutes. That if you still have some questions or unclear points that you would like to ask me, you can using the chat box. So any problems on the even the single-phase transformer or three-phase transformer I just learned today, or you need time to digest what I talked today, or you can take easy to leave the sessions, take a break.